Let's get to it. Okay, so last time I was working on a different program, but I was kind of feeling getting back into this little dependently typed programming language that I was working on a while ago. I was hoping to be done with type checking by the time I returned to the stream, but it turns out I didn't do that. Shocking. So we're just gonna do what we're up to. And where we're up to is I keep going back and forwards on how I want yeah, essentially this. This is not correct, but how I want defining these sort of types to work, particularly these parameterized and index types. I know there's prior art on this. I know how Agda and Idris do this, which is essentially they introduce a specific keyword that I mean, it introduces these inductive index parameterized. I mean, kind of, it's used for every kind of type. Well, I guess except records in Agda, but it's essentially used for every kind of type. The most generic form of types, I suppose. This felt rather unsatisfying to me. It didn't feel like that should be a primitive part of the language. If we're looking at sort of the fundamentals of intuitionistic type theory or Martin Durf type theory, it certainly didn't feel like inductive data type was a primitive in the language. So I played around with a lot with how I wanted this to look, and I was unhappy with all of them. And eventually I decided, hey, let's dig up these papers that he wrote. Let's try to figure out how he would do the vector type. Unfortunately, vector is not a mathematical, well, the notion of a vector from computer science is not really something that the mathematics side of type theory gives a shit about, so no one ever constructs it. They usually construct the natural numbers and the bounded, or the finite numbers, I guess, or all numbers less than n. So I read through these papers. This one's mostly concerned with the kind of execution semantics of how you do this translation. And pretty much the whole paper is just saying that, like, hey, if you pattern match on things, then you can get this way of executing that makes sense. Fine, whatever. Fair enough. So I went back one more paper. And you go through. And he's talking about defining the natural numbers. The abstractions described so far still do not allow us to define enough type-valued functions. For example, we want to be able to define equality between natural numbers by this schemata. So this is defining the natural numbers, essentially, well, equality of the natural numbers to be more precise, by pattern matching on the various kind of constructors, right? So you've got 0 and you've got the successor function. When he introduces this successor function somewhere, it's probably not this high. Yeah, here it is. He just says this successor function exists, right? So we have a type of the natural numbers, which is in universe 0. And we can just conclude that's true. And from the type natural numbers, which we might as well say is here, what we can conclude is that both 0 is a natural number. We'll add one more separate rule, and then from n, which is of type u0, and of n, which is of type n, we can conclude that Sn is an n. Right, so essentially what he's doing here is he's not really defining like a closed form, I guess you might call it, of what the natural numbers are. He's just sort of saying the natural numbers exist, and we're just going to give some examples of them. And what the natural numbers are is it's just anything that we say is a natural number is a natural number. So this is okay. We could do this in our language. The main problem is it's hard to know what your primitives are. Like when you're pattern matching on the natural numbers, you really want to pattern match on 0 and the successor. But if we conclude that, if we have the natural numbers, then, okay, I'm going to be abusive with my notation. We can conclude that S 0. We can conclude that this is a natural number. And a sort of question arises is, how do you know that this is not a primitive? And you might say, well, obviously because this S comes from here. But how do you do that in general? Like in this case, you just kind of look at it and you go, well, the 0 comes from here, the S comes from here, and this is a composition of two things which can be broken down. Fair enough. But the general case of like, if you have a vector which is sort of morally a function from well, we probably wouldn't write it this way. You would probably write it as, if we have an A that's in U0 and we have an N that's a natural number, then we'll say that vect of AN is a type. And okay, we can do that. That's fine. And then we need to describe the constructors of vect. Okay, so we want nil. So if we have A, which is a U0, N, which is an N, I guess we don't need any more. We can, from there, we want to be able to conclude that vect A 0 is, no, wrong, nope. We want to be able to conclude that nil is of type vect A 0. And then what else do we want? We want to be able to, if we have an A in U0 and an N in the natural numbers, we want to be able to conclude that cons and an A, which is an A, and a V, which is a vect AN, then we want to be able to conclude that cons of A and V is a vect A Sn, or n plus 1. Okay, that's all well and good. Sounds great. So now let's try to convert this down into code. Right, if we were to try to imaginarily compile in our mind all this stuff to code. I don't think this is a good example of that. No, it's not. So if we tried to compile this down to code, we would want, all right, vect should be some sort of primitive type. So we want to say that vect is of type, well, I guess it goes from here to, and then we get a natural number, and then if you give us these two things, you can get back a type. And how would we try to define that? That's the tricky part. How do we define what vect is? So we'll continue with this open form. So we'll say we're not defining vect. Vect is just whatever happens to be a vect. Okay. So then we go nil. Well, we need to get our A, but then after that, we can get a vect a0. And then our cons, we need an a, whoops, we need an n, we need a vect an, and then from that you can get a vect a successor of n. Okay, so these ones we do have to define somehow. It's not enough just to have their types. We need to be able to construct a vector somehow. So we need to be able to use these. Well, how do we define nil? Well, we could start with taking in our parameter. And then what do we get back? Well, in some sense, nil is a primitive symbol. It's not really, like, it's not composed of anything else. It's kind of just, it's a symbol that means this thing, right? It's a vector of length 0. So we should somehow mark it as primitive. Alternatively, because then we have this problem, right? So nil is a function. Or let's do cons first. We'll come back to that. So we can say cons is give me a u0, give me an n, then give me an a, give me a vector. And then what do we do for this one? How do we define this? Well, we want to be able to pattern match on all these things. And again, it's kind of just a primitive. All we're saying is that if you are able to supply these things, then we're just going to say that's what a cons cell is. Right? If you give me a vector and an a, well, that's all a cons cell is. It's just those two things. Cons is, in some sense, just a symbol that signifies that we have those two things. So we might as well make that primitive as well. But we need some way to signify that we hold these two values. Because currently, cons is just a function, right? So cons, if we write the type of it, it's a function from, well, a, which is u0, to n, which is an n, whoops, to an a, to a vect a n, to a like that. So if we tried to actually call this, if we went cons of I don't know, we'll just do a vector of natural numbers of size 2, and then we want to put 7 on the front of it, and here I guess we want a nil vector of natural numbers. Right, so this is of type vect a, this should be 1, not 2. Of vect a2. And we can give it a variable. We can call it vs equals, this is our vector, vs. And then what happens if we want to match, right? What happens if we want to match on vs? Somehow, cons needs a way of knowing in some way that it should be remembering all this stuff. It should be remembering all these input variables. But really, hang on, does it really need to remember all the input variables? We kind of only really care about the cons cell and the remaining vector, like the head and the remaining. We actually kind of don't really care about remembering a and n. That's just part of the type signature.